Okay, so welcome to section 9.1, which is systems of linear equations. In two variables. In two variables, we'll get to 3 in the next section. So these two variables are usually x and y. So let's recall. That a line is of the form y is equal to mx plus b. So note, standard form of a line is given by I'll do it here, ax plus by is equal to c, where a, b, and c are real numbers. And also note that the exponent on x and the exponent on y are 1. Hence, these are lines, linear equations. So let's consider, remember, if something has an exponent of 1, its graph is a line. So I'm going to do 3 x and y coordinate axes. So let's go ahead and do this. X and y coordinate axes. So I'm going to cut and paste this 3 times. Don't know why I can never do this evenly. Okay, so x and y. Hopefully I can fit 3 of those. Copy and paste. 2. 3. Yes, I can. Wow. Just barely. Why is it not clicking to the grid? Okay, I guess it doesn't want to do that anymore. Okay, so let's consider something like so. Let's say this is our first line. Let's call it line 1 or L sub 1. And maybe this is my second line. Let's call it line 2 or L sub 2. Okay, notice that these intersect in a single point. And I will call that point x comma y. So they share a single point. So 1 point in common. Okay, well, I feel like I'm going to sneeze. Pardon me if I do. No, that was a silly sneeze. I'm sitting in a room with ant poison. Okay, let's call this line 1. And let's have another line that's parallel to it. Call it line 2. It should be obvious that these have no points or no shared points, right? So actually, let me do this in a different color. So no shared points. And that's in the case of line 1 parallel to line 2. Okay, now let's do another. Let's say we have line 1 here. But let's say we also have line 2 here. So line 2. So in this case, they are the same line. So, how do I want to say this? All points. All points. Of course, I want to do it with this. All points in common. All points in common. With an emphasis on all. And that's in the case when they're equal, namely when line 1 is exactly the same as line 2. They share all points. So a single point, no points when they're parallel, and all points when they're the same. Okay. So definition. Oh boy, I wanted autocorrect. It's like it got rid of all the cool stuff. Okay, so a linear system. That's what we're defining, a linear system. Is a set of lines, usually 2 for 2 variables, but it could be more. Is a set of lines, the solution to which is the set of all points they have in common. Okay, so above here we have 3 linear systems. In the first case, there's 2 lines, and there's only a single point in common. So we would have a point solution, one single solution. In the second case, in the parallel lines, they have no points in common, hence there's no solution. And in the last case, they're the same line, so they have all points in common, which is infinitely many solutions. Okay, so let's note something about the terminology of a single point solution, no solution, and infinitely many solutions. So each of these has a different name. So first, an independent system. So an independent system has a single solution, x comma y. Okay, an inconsistent system has no points in common. So that would be line 1 parallel to line 2. And last but not least, what about if they have all points in common? That's called a dependent system. Dependent, and you can think of dependent because they're one and the same. One cannot move without the other. They are the same thing. So they're very, very dependent on one another because they are one another. So a dependent system has all points in common. And of course that's a case when line 1 is equal to line 2. Okay, so for example, solve the following systems. Solve the following linear systems. Graphically. Sorry, I thought I felt an ant. Okay, so number 1, let's say we have 3x minus 2y is equal to 6. And what shall we do? Let's do x plus 2y is equal to 2 for the other guy. So let's solve this system graphically. Okay, so x and y coordinate axes. No, not drawn very well. So x and y. Let's do 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. Okay, so let's look at the first line, namely 3x minus 2y is equal to 6. The easiest way to do it is let x equals to 0. And when we do that, we get negative 2y equals 6, or y is negative 3. So y is negative 3 is 1 point. Then we let y equals to 0. That means that 3x is equal to 6, or x is equal to 2. So now I have 2 points on the line. 2 points determine a line. So I can just go ahead and draw these guys. Hopefully that's somewhat okay. No, let's see, maybe I can edit it. Yes, I can. Oh, that's nice. Okay, good. Looks a bit better. Okay, nice. Nice what I can do with Notability. Okay, so I'll call this line 1. Now let's look at the second line, the purple guy. Why is this not auto-correcting? Come on. Really? There we go. Okay, so in the first case, I'm going to let x equals to 0. When I do that, I get 2y is equal to 2, which means that y is equal to 1, so that's 1 point on there. In the second case, I'll let y equals to 0, in which case we get x is equal to 2. Okay. Oh, look at that. I can see right away where. Well, if I could draw it well, please autocorrect. There we go. So this is line 2. Notice that they have this point here at, what's that point? It's 2, 0. So that's a solution. So the point they have in common is 2, 0. Okay, I'm just going to leave it unauto-corrected. That's sufficient. Okay, let's do another one. So number 2. Let's see, what do I have here? Let's do the system. Let's do x plus 3y is equal to 6, or x minus y is equal to 2. So once again, x and y coordinate axes. X and y. Let's do 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay. So let's look at the first line. And let's let x equals to 0. That gives us 3y is equal to 6, or y is equal to 2. So that's our first point. Then let's let y equals to 0. And that gives us x is equal to 6. 1, 2, 3, 4, 5, 6. Okay, so that looks like it's going to be something like so. There we go. Call this line 1. Okay, so now let's look at line 2. So first I'm going to let x equals to 0, which gives me negative y is 2, which means that y is negative 2. So that's my first point. Then I'm going to let y equals to 0, which gives me x equals to 2. Okay, that's good. I can do that. Okay, so this is line 2. And so it looks like the point they share here is at 3, 1. So I claim the solution for this will be 3, 1. Yeah, there we go, finally. Okay, so let's do another one. Number 3. Let's do the system. 2x minus y is equal to 4, and 6x minus 3y is equal to 6. Okay, so x and y coordinate axes. Nope, okay, come on. Yeah, there we go. Okay. So x and y. Let's do 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. Okay, so let's look at line 1. And I'm going to let x equals to 0, which means that negative y is equal to 4. Oh, y is negative 4. Did I not do that down far enough? No, I didn't. Okay, let's let y equals to 0. Then we get 2x is 4, which means that x is 2. Okay, so there we go. Call this line 1. Okay, actually maybe I don't need to make it so long. We get the idea. Okay, now let's look at line 2. So we have, let's let x equals to 0, which means that negative 3y is 6, or y is negative 2. And let's let y equals to 0. That gives us 6x is 6, which means that x is 1. Okay, interesting. Let's see what happens here. Looks like the slope is exactly the same. Rise. Let me get that a bit better. There we go. Okay. These lines are parallel. No solution. So these are parallel. So line 1 is parallel to line 2. So that implies no solution. And remember, no solution is this symbol, the empty set. No solution. Okay. Let's do one more for good measure, shall we? Number 4. So let's say we have the system. Negative x plus 2y is equal to 3. Or 2x minus 4y is equal to negative 6. Okay, so x and y coordinate axes. X and y. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay. So let's look at this first case. So we have negative x plus 2y is equal to 3, which means that 2y is x plus 3, which means that y is equal to 1/2 x plus 3/2. So now this is in mx plus b form. I know my y-intercept is 3/2, and I rise 1, run 2. Rise 1, run 2. Rise 1, run 2. So it's going to look something like so. If I can get this right. Okay. So line 1. Let's look at line 2. We have 2x minus 4y is negative 6, which means negative 4y is negative 2x minus 6 dividing by 4, negative 4, we get y is 1/2 x plus 3/2. Okay, that's exactly the same line, right? Okay, so line 2 is equal to line 1, so there's infinitely many solutions. So infinitely many solutions. But how do I write the solution set? The solution set is as follows. The set of all x comma y such that, and I can choose which one I want. I can either choose the first equation or the second. So let's choose the first. Such that negative x plus 2y. Negative x, what am I saying? Can't speak and write at the same time. Negative x plus 2y is equal to 3. Now the reason it doesn't matter which one I choose is because they're both the same line. So they will both reduce to the same equation, regardless of which one you choose. Okay, so that's how we would annotate the two lines that are exactly the same. Okay, so there's other ways of solving a system that don't involve graphing. So let's first look at what I think is the worst way, and that's called substitution. So solving a system by substitution. So I'll show you the steps, and we'll go over a few of these. Okay, so step 1. So choose which variable you want to solve for, or want to, solve for. Okay, so here's the hint. Find, if possible, a variable with coefficient 1. Coefficient 1. And that's what you're going to choose. So number 2. So solve for that variable. Once you've chosen it. So number 3. But choosing it can be the most important part. So plug the equivalent of that variable into the other equation. So plug the equivalent of that variable into the other equation. Okay. Number 4, solve for the remaining variable. And number 5 will be to back substitute. To solve for initial variable. Variable. Okay, like I said, this is not my favorite method, but we won't get to the really good stuff till the end of this chapter. So for example, use substitution to solve the following systems. Number 1, let's say we have 2x minus 3y is equal to negative 7, and x plus 4y is equal to 13. Okay, so right away, let me draw this bracket a bit better. I notice that there's a coefficient of 1 on this variable here. So what I'm going to do, I'm going to rewrite the system. So 2x minus 3y is equal to negative 7, and x plus 4y is equal to 13. And I'm going to take and rewrite this. X plus 4y is equal to 13. And I'm going to solve for x. So I claim that x is 13 minus 4y. Then I'm going to take the first equation, and maybe I should color code it. Let's make this purple, which means I'll have to make this something else like pink. There we go. Okay. So what I'm going to do now is I'm going to take the 2x minus 3y equals to negative 7 and plug in the value I got, which was 13 minus 4y. That's its equivalent, right? And now I can distribute. So what do I get? 2 times 13 is 26. 2 times 4 is 8. Okay, now I can combine like terms. This is 26 minus 11y is negative 7. Now I can subtract 26, so I get negative 11y. So 26 plus 7 is 33. Sorry, negative 33, because they're both negative, which means dividing y must be positive 3. Okay, so what we do now is we back substitute. So I'm going to take this, and I'm going to plug this y right into here to find x. So I claim that x is going to be 13 minus 4 times y, which is 3. So x is going to be 13 minus 12, so x is going to be 1. So if x is 1, if x is 1, then the point is 1 comma 3, x comma y. That is the solution. So this is a consistent and independent solution. Okay, let's do another one. Number 2. Let's do 5x plus y is equal to 6. And 2x minus 5y is equal to negative 3. So right away I see that there's a coefficient of 1 attached to that y. So that's the one I'm going to concern myself with. So let's see. I'll have, 5x plus 1y is equal to 6. And 2x, why is it not working? 2x minus 5y is equal to negative 3. Okay, so right away, from this first equation, I can go ahead and solve for y. And I claim that y is going to be 6 minus 5x. So now I can use the second equation. Plug in, I will get 2x minus 5 times y, which is 6 minus 5x, is equal to negative 3. So we get 2x. Let's go ahead and distribute the negative 5. Minus 30 plus 25x is negative 3. So how many x's do I have? I have 27 x's. And if I add 30, it will be 27. So I get that x is equal to 1. So now I can plug this back into here. And I get that y is equal to 6 minus 5 times 1, which which is 6 minus 5, or 1. So the point where these two meet, is going to be 1 comma 1. So that's a solution. And it is an independent system because we have a single point. Okay, so far so good. Hopefully this is making sense. Let's do some more. So number 3. Let's say we have, let's do, I don't know, what should we do? How about x minus 4y is equal to 11, and minus 3x minus 12y is equal to negative 11. Okay, so I notice that there's a coefficient of 1 attached to that x, so that's the one I'm going to focus on. So we have x minus 4y is equal to 11, but we also have minus 3x minus 12y is equal to negative 11. Okay, so let's do this and dashed. Okay, I claim that x is going to be 11 plus 4y. Now I can plug that into the equation below, and I get negative 3 times x, which is 11, plus 4y, minus 12y will be negative 11. So let's distribute. So we get negative 33 minus 12y. Minus 12y is negative 11. Let's add 33 to both sides and combine like terms. So I claim this is negative 24y is equal to, well, what's 33 minus 11? It's 22. Oh boy, I didn't think this out well. Pardon me. So y is going to be negative 22 over 24. Well, that reduces because 2 goes into 22 11 times and into 24 12 times. Okay, so now I can plug this value of y back up here. So I get 11 plus 4 times negative 11 over 12. So this is 11 minus 44 over 12. I'm not going to have room. I don't like that. Let me move this down here. So let's go over here. X was 11 plus 4y. So we get x is equal to 11 plus 4 times negative 11 over 12. So x is going to be 11 minus 44 over 12. So the common denominator is 12. So 11 times 12 is what? Well, 12 times 12 is 144. So if I subtract 12 from 144, I get 132 minus 44 all over 12. Okay, well, 32, what's the difference of 44 and 32? And that's 12. So I'm going to be 12 less than 100. So 12 less than 100 is 88. So this is 88 over 12. Well, does 4 go into 88? It does. It goes in 22 times. And 4 goes into 12 3 times. 22 over 3. Interesting. Okay, so what do we have? We have as our solution the point x, 22 over 3, y, negative 11 over 12. Terrible numbers. Don't worry. Hopefully we won't see these terrible things, but you get the idea. Okay, yeah, let's move on from substitution, shall we? Because substitution is terrible. Let's move on to something much more elegant, and that's elimination. So solving a system. Solving a system by elimination. This is so much better. Elimination. Okay, so step 1. Determine which variable you wish to eliminate. Step 2. Multiply each equation by the coefficient of that variable in the other equation. Okay. Step 3 will be to add or subtract as necessary. To eliminate the variable. Okay. Step 4 is to solve for the remaining variable. Okay, so step 5 is to either back substitute or repeat the above. To find the other variable. Okay, so what do I mean by all of this? This is actually easier done than said. So, for example, solve the following systems by elimination. So solve the following linear systems by elimination. Okay, so system number 1. Let's say we have 2x minus 3y is equal to negative 6, and 5x plus 2y is equal to, say, 23. Pardon me. Okay, so what I'm going to do, I'm going to rewrite the system. 2x minus 3y is negative 6. Pardon me. And let's do 5x plus 2y is equal to 23. And I'm going to call this guy pink. Maybe yellow. Okay, so let's say I want to eliminate x. If I want to eliminate x, then I have to multiply the first equation through by the coefficient of x in the other equation. So the coefficient of x in the second equation is 5, and in the first is 2. So when I do this, what I get is the system of equations. Let's see, 10x minus 15y is equal to negative 30. 10x, oops, wrong color, hold on. 10x plus 4y is equal to 46. Okay, so add or subtract as necessary to eliminate. Well, I wanted to eliminate x, so in order to do that, I would have to subtract 10 from 10. So 10 minus 10 goes away, that's 0. Distributing the negative to each term. Actually, let me do that in a dashed line. Distributing the negative to each term. We will have 15 minus 4, sorry, negative 15 minus 4 is negative 19y. Negative 30 minus 46 is going to be 9 minus 76. Okay, well, how many times does 19 go into 76? Well, what's interesting is 76 is 4 shy of 80, and 20 times 4 is 80. So I claim that y is positive 4. Okay, so I've solved for y using elimination. What I could do at this point is go back and solve and back substitute, but I'm going to do this same process for x now, to solve for x using elimination. Okay, so I'm going to start off with the equation 2x minus 3y is equal to negative 6. And 5x plus 2y is equal to 23. But now instead of eliminating x, I'm going to eliminate y. Oops, wrong. Okay, so what I'm going to do is I'll multiply the first equation by the coefficient of y in the second. And I'll multiply the second equation by the coefficient of y in the first. Okay. Actually, I'm going to do it in absolute value so I don't have to deal with negatives. Let's make this a positive 3. Because when I do that, you'll see what'll happen. Okay, so multiplying the first equation by 2, we get 4x minus 6y is equal to negative 12. Multiplying the second equation by 3, we get 15x plus 6y is equal to, let's see, 69. Okay, notice now, in order to eliminate y, all I have to do is add the two equations together. So when I do that, 4 and 15 is 19x is equal to 69 minus 12 will be 57. Okay, well 57 is 3 shy of 60. And 20 times 3 is 60. So I claim that x is 3. You can check my work. But I claim the point where these two meet is 3, 4. And that's the solution to this system of equations. It is independent and consistent. Okay, let's do another one via elimination, which is so lovely. Just gotta love it. Okay, so the second system, let's do x plus 4y is equal to, let's say, 15. And let's do negative 2x plus y is equal to negative 12. Okay, so rewriting the system. So we have x plus 4y is equal to 15. Then we have negative 2x plus y is equal to negative 12. So if I eliminate x, I'll multiply by 2, the coefficient, without the negative this time, of x in the denominator, there's no denominator, in the second equation, and 1, the coefficient of x in the first equation. So what do we get? Let me tell you, sniffing a bug killer in an enclosed room is not good for your brain. Don't do it. Okay, so where was I? So multiplying the first equation by 2, we get 2x plus 8y is 30. And the second equation, multiplying it by 1, we just rewrite the equation. So notice these are going to reduce nicely if I just add these two equations. And doing so gives us 8y plus 1y is 9y. 30 minus 12 is 18, so y is 2. Okay, so let's do the same thing again for x. So I start off with my system. So I have x plus 4y is equal to 15, and negative 2x plus y is equal to negative 12. So I multiply the first equation by the coefficient of y in the second, and the second equation by the coefficient of y in the first. So what this gives me then is just the first equation, x plus 4y is equal to 15, and the second equation now becomes negative 8x plus 4y is negative 48. But notice I'll need to negate this in order for the y's to sum to 0. If I distribute the negative sign everywhere. Okay, so x plus 8x is 9x. The 4y's reduced to 0. 15 plus 48 is going to be 63. Well, 9 goes into 63 7 times, so I claim the solution here. X comma y is going to be 7 comma 2. Okay. That's the point where these two lines intersect. Okay, let's do third time's a charm for this section. Okay, so we have 5x minus 10y is equal to 20, and negative 3x plus 6y is equal to negative 12. Okay, let's rewrite the system. We have 5x minus 10y is 20, pardon me. And the second equation is minus 3x plus 6y is equal to negative 12. Okay. I notice that the first equation can be divided by 5, and the second equation by 3. So that's interesting. So if I did that, what would happen? Let's go ahead and divide the first equation through by 5. Second equation through by 3. Just so I can simplify my life. Okay, so simplifying before I start multiplying big numbers like 20 and 12 and things like this. Let's see, this reduces to x minus 2y is equal to 4. And the second equation will be negative x plus 2y is equal to negative 4. That's interesting, because at this point, I can just add these two equations together to get rid of x, and y, and the constant 4. So I get 0 is equal to 0, and that's always true, right? Always true. So that means this is a dependent system. I can see that these two equations are actually the same. If I multiply through by negative 1, they're both the same. So therefore, the solution, will be the set of all points x comma y, such that, well, use whichever equation you like. Let's use the first one. 5x minus 10y is equal to 20. Could have used the second one. We could have used any of the simplified forms. There's infinitely many solutions here. Let's try another one. Let me move this up a bit, see if I can. Number 4. Do I have enough room? I don't know. So let's say we had the system 2x minus 3y equals 7, or negative 4x plus 6y is equal to 7, something like this. Okay, so let's look at the system. 2x minus 3y is equal to 7, and negative 4x plus 6y is equal to 7. So I'm going to go ahead and eliminate x. I'll multiply the top equation by 4, the bottom equation by 2. So what does this give us? This gives us 8x minus 12y is equal to 7 times 4 is 28. And the second equation multiplied by 2 will be negative 8x plus 12y will be equal to 14. Okay, so I noticed to eliminate x, I can just add these two equations. So the x is reduced, but the y is also reduced. So I get 0 on the left, but what do I get on the right? I get 42 on the right. 0 is equal to 42? That's impossible. This is absolutely not right. This is an inconsistent, right? So this is no solution. This is a circle with a line through it. Circle with a line through it, no solution. Okay, that is the solution. No solution. Okay, so 0 equals to 0 is always true. And that's infinitely many solutions. 0 equals to a number, a non-zero number, is never true. 0 cannot be equal to something that's non-zero. So that is no solution. Okay, I think I'm going to stop it there for this section, and I will see you in the analogous section for 3x3 systems in a moment.